Hi, everyone, and welcome to our next presentation in our Your Universe series. The past 2 weeks, we've been talking all about Jupiter, and today we have two guests that I'm really excited to have speak today about the Radio Jove project at Ball State. We have Ball State's professor from a Ball State professor from the Department of Physics and Astronomy, Dr. Todd Vaccaro, and we have an undergraduate student from Ball State, Nicolette Terrasciano. And we also have Rachel Williamson today helping out with answering any questions or any comments in the chat. So if you have anything you want to know more about, then just ask that in the chat and Rachel will be able to help you out there. For the past 2 weeks, we've been exploring Jupiter, the largest planet in our solar system. And we've been getting a lot of great images about or of Jupiter lately with the Juno spacecraft that's currently in orbit around the planet. And it's been observing the planet from above to help scientists learn more about the planet's atmosphere, the magnetic fields that are around Jupiter, the structure and the core of the planet and its origin to better help us understand many things in our universe, including how our solar system came to be. And we've also been exploring some of the 79 confirmed moons around Jupiter, including the largest four moons, are the four largest moons, Io, Europa, Ganymede, and Callisto, or what we call the Galilean moons. And we can explore all of these things in visible light. And some of these photos are taken using visible light, so light we can see with our eyes. But of course, cameras can capture more detail and we can enhance photos to see more. But we can also explore the planet and the moons in radio light. And that's what our guests are going to be talking to you about today, and the Radio Jove project at Ball State. So I'm going to turn it over to Nicolette for the first part of this presentation. So Nicolette, I'm going to go ahead and stop sharing my screen and let you unmute yourself, start your video, and start sharing your presentation.
Okay, good morning. So let's get started here. So I'm mainly going to be talking about the history of Radio Jove today. Like many objects in our night sky, everything has a beginning. So I'm going to be talking about the very beginning of it all and where it all started. So before we begin, let's talk about what is Radio Jove. It must be a very new title for most of our viewers today. So Radio Jove uses technology and strategies found in radio astronomy to observe aspects of Jupiter. Some examples are its constant storms, its auroras, or just the Jovian system altogether. So the moons, the magnetic field of Jupiter, and Jupiter itself. So when it comes to observing radio emissions, the radio emissions come from charged particles that interact with Jupiter's magnetic system. Most of the emissions that we are going to be able to observe on Earth are going to be 4 to 39.5 megahertz. And if you look at this chart over here, it's most of our readings, or at least where this peak is, if you can see my cursor, is going to be in the decametric scale. That means it's going to be 10 meters for every 1 decameter. You can also see that the solid lines represent the frequencies that you will get, and the dotted lines is where you won't be getting many readings. And these solid lines go out of the spectrum of 4 and 39.5 megahertz. You can get these readings, but you have to have the ideal conditions. Perfect weather, the sun has to be in the right position, the Jovian system has to be in the right conditions, so everything has to be perfect, and that's very rare. So it's not as common. So your common ground is going to be between 4 to 39.5 megahertz. So all of this in the Radio Jove system really started in the year 1955. Radio astronomy was extremely popular, and a lot of astronomers were using radio waves to identify objects in the sky. In this case, certain radio astronomers were using radio astronomy to collect data on the Crab Nebula, which is pictured here. It's very beautiful. These two astronomers were Kenneth Franklin and Bernard Burke. They are from the Carnegie Institution in Washington, D.C., and they were using the Crab Nebula to test out their new antenna array of their own. So they made it. And this thing is quite big. I don't know if you'll be able to see it in this picture. I have many pictures. But if you can follow my cursor, if you can see it, you'll see these lines, these poles, and all these wires sticking up out of the ground. That is the antenna array that they're using to get the radio waves from the Crab Nebula. It's quite big. In this picture, you can see it a little better. The red lines are the poles I was pointing out earlier. That is 96 acres large. It's quite massive. So they were collecting a lot of data, and a little bit of time goes by, and they started to notice some significant noise in their data, more than usual. They initially thought it might have just been some interference on Earth, which is understandable. Earth has a lot of radio waves traveling across the world, whether it's the music radio you listen to or other kinds of machinery that may or may not give off radio waves. However, they gathered some more data, and they were able to develop a pattern. And those who are involved in science know that a pattern can usually lead to a relationship. Some more data came in, and they noticed that the noise started to occur roughly 4 minutes earlier every night. This could lead to the Sidereal Day and Solar Day. So for those who don't know, a solar day is what we go off of, the rotational period with respect to the sun. So that's our 24-hour mark, how we track every day. The sidereal day is the rotational period with respect to the stars. This is why you can go to the same place, same hill, with the same little blanket that you'll lay out and look at the same spot in the sky, and the Big Dipper is not going to be in the same spot. The stars tend to move across the sky. This is what we're talking about with respect to the stars. And this time is slightly different than solar day. It's 4 minutes shorter, so 23 hours and 56 minutes. You can see with the little chart here, you have a little person, and he is on the solar day with the 24 hours, and this little person here is on the sidereal day, 23 hours and 56 minutes. So after some careful consideration, they realized that the object did not travel like stars do in the night sky. It was slightly off in a way. This helped them eliminate what the strange noise could be. So it wasn't anything relating to stars. So no stars, no galaxies, and nebulas was also not possible. Franklin and Burke later realized that there was an object that was close to the Crab Nebula that around the time that the noise was occurring. And by close, I do not mean that the Crab Nebula was right next door to Jupiter. Close in view. Sometimes if you look through a telescope, Venus and Mars will look very, very close to each other like they're next door neighbors. However, that's not how it appears in our solar system. And that's what I mean by close. And the object that they saw that was close was Jupiter. So on April 6th in 1955, a meeting was held with the American Astronomical Society, and there Franklin and Burke announced that Jupiter gives off radio emissions. And this changed the world of astronomy for a very long time. A lot of astronomers looked back on old data or past experiments to see if they had Jupiter-like noise and fluctuations like Burke and Franklin did with their experiments. One astronomer in particular, C.A. Shane, discovered that he had Jupiter-like noise in his data that he recorded 5 years prior, which is actually pretty fascinating. This all led to extensive data research on Jupiter and many other objects in the sky and many other discoveries. And this is my works cited.
Thank you so much, Nicolette. And now we're going to have Dr. Vaccaro continue the presentation, speaking more about the Radio Jove project at Ball State University. And if you're just joining us, we just heard from undergraduate student from Ball State, Nicolette Terrasciano. Thank you so much, Nicolette.
Okay, I'm on.
You're good, yeah.
Cool. All right, so go ahead and share screen. And let me get to my... Oh, why is it jumping around? Make sure that I have my audio on. Okay, looks like I have that set. All right. All right, well, good morning or afternoon, or it's almost afternoon. So Radio Jove project at Ball State University, just as sort of a disclosure of my involvement with Radio Jove, I've worked with the Radio Jove project in a couple different institutions over the past almost 13 years. But the project itself at Ball State is what I'll focus on, but I have some information from previous institutions and previous builds. So the Radio Jove project is not something brand new. It's been around for a while, as we'll discuss in the history of the project itself. And so moving along with what is Radio Jove, you heard basically some of the historical aspects of the radio emissions with respect to the planet Jupiter being discovered back in 1955. But the Radio Jove project, of course, Jove itself might not be quite so obvious as why this name was actually chosen. Jove is just another name for Jupiter in Roman mythology. So Jupiter, or Jove, in Roman mythology is the king of the gods, and of course the equivalent in Greek mythology would be Zeus. But the Jove name made some sense, and in addition, one of the things that I didn't even recognize until recently was, why is Jove always in all caps? And when I think I first noticed it when Nicolette did her presentation once before in a class of ours. I noticed it and I was like, why is she yelling Jove at me all the time? And so it turns out that there is a significance to the all caps of the Jove name, because it basically represents sort of the 4 letters of a call sign for a radio station. So that was just sort of the convention that was used, and something I actually just didn't realize until recently myself. And then a friend of mine who works with the Radio Jove project actually mentioned to me recently that they kind of jokingly refer to Jove, we're they're the great red spot on your radio dial. And so, of course, we're talking about radio emissions. And so the goal of the Radio Jove project is to build a antenna to detect these radio emissions from the planet Jupiter. So what is the Radio Jove project per se? This is one of the standard flyers that if you look up the Radio Jove project, that you see all the time, and this kind of lays out who the sponsors of this project were back in around 2000. So this project is about 20 years old as far as what we'll be talking about today. And the team, some of the contributors obviously involve NASA. We'll talk a little bit about what their current involvement is, and some of these other institutions like Raytheon, University of Florida, Radio Sky Publishing, I'll mention a little bit about that today, and some of these other schools like University of Hawaii. And then, of course, some of the names associated with it, and there'll be some names that we'll mention at the very end. Jim Thyman and Chuck Higgins are the sort of contact people for this. And so these should be good contact information for them. So again, my expertise is really more in optical astronomy, but I got interested in Radio Jove because it seemed like a fascinating area of astronomy to really get students and the general public involved in. And so that's why I thought this would make a pretty good sort of talk and a project to run again here at Ball State. And so what the Radio Jove project actually is a sort of hands-on experiential sort of learning, as well as a research tool that allows for the observation of radio signals coming from natural sources like Jupiter. That's obviously its namesake, but it can also pick up radio signals from activity on the sun. And so there's solar activity on the sun, flares and sunspots and prominences and all these interesting features that you see perhaps in this picture down here that look like they're above the surface of the sun. And they can actually emit quite a wide range of frequencies of light, not just visible light. And so radio is just another form of light. And that's something that if you're not familiar with sort of physics or astronomy in general, when people think of radio, a lot of times they think of radio stations. They tune in with their stereo receivers in their car, in their homes, and that when they do that, they're producing or listening to sound. And so you have to realize that that is the electronics of your receiver converting a radio signal, which is actually a form of light, by an antenna, and converting it into sound that comes out of your speakers. Now, we can kind of do the same thing with Radio Jove ultimately, and that's kind of interesting, but it's really important to sort of, in terms of the real physics involved, understand that we're really detecting another form of light we just can't see with our eyes. And so the sun can be a source of this, Jupiter can be a natural source of this, and then our galaxy itself, the Milky Way galaxy, is a source of radio waves. In fact, some of the very early radio astronomy that was done was very similar to what Nicolette was talking about earlier. If you detect a signal that seems to be coming at a regular sort of increases in strength over periods of time that are more like 23 hours and 56 minutes, that 4 hour less than the 24-hour solar day, you know that it's something that's great distances and some fixture of the what we might refer to as the celestial sphere, right? Not even something necessarily solar system oriented. And so there's some difference in times for those as well, because the planets move in their own orbits and they're a lot closer. So the center part of the galaxy, for example, would be associated with a large source of radio signal coming from the supermassive black hole that we know exists at the center of the Milky Way galaxy. And that's a fascinating, discussion and topic for some other presentation. So I'll focus primarily on some of the Jupiter aspects today. But the Radio Jove project itself is a rather flexible tool for really exploring some of this stuff. And then we'll actually see we can use some of the information to tell us something about the Earth's atmosphere as well, and what's going on terrestrially as well as off Earth. So what is the source of Jupiter's radio signals that it does emit? And as Nicolette actually mentioned earlier, charged particles interacting with Jupiter's magnetic field are really the primary source. And the Radio Jove design that we'll talk about, the telescope design that you can get the plans to build, this is the type of signal or source of signal that we're looking at. We're looking at cyclotron radiation. Okay, and so cyclotron radiation is charged particles, mostly electrons, that get accelerated in the magnetic field of Jupiter. And Jupiter's magnetic field is pretty strong, and it's pretty extensive. If you were watching last week's presentation on Jupiter, there was a lot about Juno, the spacecraft that's currently orbiting Jupiter. One of the primary missions of the Juno satellite is to not only orbit Jupiter on a repeated basis and get some information about gravity, but to dive in through these magnetic fields. And it was built in such a way to withstand some of the charges and things that it would actually fly through, somewhat like the Van Allen belts of the Earth, but much, much stronger. And so when you move these charged particles around in these sort of helical orbits, they zigzag around and whip around these magnetic fields, the acceleration of these charged particles cause the emission of photons, and the photons have certain frequencies. And the particular frequency of interest for us is one that produces a wavelength of radio emission in the decametric. And so that decametric radiation that was mentioned earlier today is the DAM. So DAM is for decametric. We're talking tens of meters of wavelength, physical length of the wavelength of light. And that actually falls into the sort of frequency range of, I would say, sort of the shortwave radio band. So if you're a shortwave radio person or a ham radio operator, you probably know exactly what I'm talking about. And so this is really, in many cases, the largest number of people that work within the Radio Jove project are enthusiasts, radio enthusiasts, and ham operators. And so they would probably know more than I do about some of this stuff in terms of the different frequencies and what you can do with it on a terrestrial basis. This is sort of a diagram. We don't have to go through too much of the details here, but one of the interesting things in this sort of diagram is showing the interaction between one of the inner moons, well, the innermost moon of Jupiter, Io. So this is sort of looking from a perspective of the Earth out towards Jupiter, and this sort of gray area is the area called the torus, the Io torus. It's sort of a ring of material and an area where Io is actually outgassing as a very volcanically active planet, and so there's a lot of material that is sort of put into this sort of hoop around Jupiter. And being very close to Jupiter, to give you an idea of just how close it is, at least in terms of its orbital period, it only takes about 42 hours for Io to orbit around Jupiter once. So it's close enough to this massive planet that it's whipping around very quickly, just a couple days. And this material can interact with the magnetic field. So these dotted lines here and these solid curves are tracing out some of the magnetic fields from Jupiter. And they basically come out of the north geographic pole of Jupiter itself. So these arrows here for M is the magnetic field pole, which is only slightly off from the geographic rotational axis pole indicated by this Greek letter omega here. And then Jupiter itself actually spins around on its axis quite quickly. It rotates once every 10 hours. So less than half the time it takes for the Earth to spin around on its axis, Jupiter is going to be moving around much quicker. And for a very large planet that's, almost a dozen times larger than Earth, that's quite impressive. And it's that combination of size and rotation and the structure of Jupiter that actually is responsible for producing the magnetic field. Now, these little cones that you see coming out of these various magnetic field lines represent the different types of radiation that are produced by the material that can be interacting with Io, or the general environment of Jupiter itself. So you have some of these things are listed as Io decametric, or non-Io decametric, or hectometer, or kilometer wavelength. And this little B here stands for broadband. So the ones that we're interested in as part of the Radio Jove project are the Io and maybe some of the non-Io decametric. Because the telescope that we're going to be talking about, the radio telescope or antenna, is actually designed to pick up or amplify these particular wavelengths of light. And most of them are the type that have some interaction with the Io material and the torus, or Io directly. So there's a couple things that interact with each other that we've learned over time that produce the signals that we detect here on Earth. So, and the cones here are primarily indicating that these forms of radiation are actually beamed in certain directions. And that's really important because when we talk about perhaps when might one go out with your radio telescope or turn it on to detect these signals, because they're not going on all the time, right? And obviously you need Jupiter up in the sky for us to be able to observe from Earth. But there's also some important timing things that we need to consider for understanding when we might go and make an observation. And it really has to do with the position of Io relative to Jupiter's magnetic field. And so there's this discussion of two different types of periodicities, the rotation and the position of orientation of Jupiter. Where is it in its rotation? And where is Io in its orbit? And when these things are just right, you can get one of these cones basically pointing towards Earth in such a way that we can pick up those signals, that beaming radiation, which is the cyclotronic radiation. One key point to mention, because someone did bring up an interesting question, cyclotron sounds very similar to another type of formation of radiation called synchrotron. And the difference between cyclotron and synchrotron is really the speed with which the particles are being accelerated. And so for cyclotron, you have the lower end of speeds that produce these decametric wavelengths, whereas if you had synchrotron, you would be moving at more maybe relativistic speeds, and the frequencies with which you would emit would be higher than the sort of Radio Jove range that we discussed, that sort of 5 to 40 megahertz. So what kind of signatures do we get from the cyclotron radiation? There's really sort of two sort of flavors. of signals that we get. And if you didn't know what you were getting, because it was described as a noise, and it really is kind of a noise when you translate that radio signal into a sound with a receiver and a set of speakers, for example. That sound that you hear is basically just different disturbances, different levels or changes in the background noise. And so for the untrained ear, you might just think, maybe it's just your electronics or just some sort of just background noise. You might not know what it is. And so this gives you a taste of what the two different types are. They come basically in long burst, L bursts, and short burst, S bursts. So pretty easy to remember, simple names. And so I have some samples of what those would be like. Now, these samples are probably going to be loud enough that I'm not going to talk over them, so I'm just going to go ahead and let them play out. So the L burst is a long burst, and they kind of sound like ocean waves. And so it sounds like the background noise is kind of surging rhythmically with almost like waves at the beach or something like that. And this is typically what we would see on a computer screen with a piece of software called Radio SkyPipe. And so it's what we call a strip chart. And it's basically telling us what our signal strength is over time. So the x-axis is just time, and this will continue to flow. And you can actually, if you were running the program and collecting data, you would see this plot being created in real time. And then you could record this data and save it for analysis sometime later. Or one of the neat things about Radio Jove, the project, is that the NASA actually maintains a database where you can sort of trim down your strip chart to where you need, just to point out where you thought you were picking up radio signals from Jupiter or some other interesting signal you wanted to archive, and you can upload it to the archive, and it can be there for other people to use in their study. So you can actually contribute by submitting your own observations as sort of a citizen scientist, which is an initiative in many different scientific endeavors. So obviously, just looking at these little peaks, you might think, well, I don't know how the heck this is supposed to sound. So this will actually give you an idea. I think I have the sound program set up to show you sort of a timeline. I'll try to keep it active. So the timeline will go across the screen and another application superimposed on top of this chart. And you can sort of follow along and sort of the time sequence down at the bottom here. So let's go ahead and turn this on. Okay, so it wasn't perfectly lined up, but I think you get the idea. And from that, this is an example of an L burst. What about a S burst? These are short bursts. You can see this looks a lot noisier, and that's because these bursts happen in very quickly and kind of sound like popcorn popping or something to that effect. Okay, so I think you get the idea there. Right, so it went beyond a little bit beyond the 60 seconds on my chart here. And so those are the two primary ones for Jupiter. As I mentioned before, solar signals can be detected as well. Generally, these are solar outbursts. And so this is a typical chart appearance. Notice that the time frame of this is relatively short. It happens very quickly, and then it tapers off over the period of about a minute or so. And so the quick rise in maybe a few seconds, and then it maintains sort of a strong level for a few seconds and then starts to drop off. This is sort of what they refer to as the shark fin pattern. And this is typically what solar signals look like on these strip charts. And so let's take a look at or listen to what these would sound like. Oops, let's cancel that. So you can get the sense of the very quick surge. And so it really just sounds like an increase in volume of the background sound, but it's really a sweeping effect of these flares occurring over many different frequencies. They usually sweep across multiple frequencies, not just the one that the Radio Jove antenna happens to be tuned at, because you have to realize that the antenna, the way it's designed, has got a receiver that is just picking up one particular frequency you're dialed into, just like you do for a radio. So for example, this particular solar burst was measured at 29.4 megahertz, which might be an extreme end of the Radio Jove tuner. It's primarily tuned for 20.1 megahertz.
Todd, we
Yes.
have a question. If you know, do you know the type of solar burst that is? Apparently,
this particular one I don't, although March 18th of 2001, that would have been around a period of, I think that was near solar maximum back then. So it probably came from something erupting near some spotted region on the sun. You might be able to go back and look at some of the archival data from something like spaceweather.com. Spaceweather.com might go back that far. You might be able to pull up an image. I mean, we could probably do that near the end and look at
sure.
What was
Riley was
there.
wondering if there's like maybe a 1 through 5 label applied to this particular solar burst, or if maybe we can figure that out later at the end. Yeah.
I don't know if this is calibrated here. I'm not sure, because this is not my data. This is just an example, so I'm not really sure which magnitude type of solar flare produced this. But I could probably double check with my sources and get back to you if you want to just drop us an email, and I can certainly look that up. I don't know off the top of my head, but that's a good question.
Great, thank you.
Sure. So what is Radio Jove? It's actually a kit. I mean, you can probably get the designs. The manual for this sort of stuff is available online at the Radio Jove website that I'll post at the end. But it's if you purchase one of these pre-made kits, you get basically this equipment you see pictured here. And so this is really, it's just a big long piece of copper wire that you cut into a couple pieces of certain length. You need to get it just the right length. The dimensions of what you set up is all about what wavelength or frequency you're trying to observe. And then you have some of these little insulators, these little white ceramic pieces that you attach things to, the wire and so forth, a power combiner. This looks like some of the stuff you might need to hook up your cable television set up with, or your your video equipment, VCR and these things. If you've ever done that, you know exactly what all this stuff is. The white cable here, this is actually coax. It's the same exact sort of stuff that, DirecTV would set up with the dish to your receiver in your house. And so a big long length of this that you cut up into different pieces. And Nicolette knows everything about all this stuff because one of her jobs during this past semester was to get this stuff and put it all together and cut it all up and attach the ends to it and everything and construct the antenna. So you get a kit, you get that stuff. You also get a receiver. This is basically the sort of heart of the whole telescope system. The antenna is basically the so-called eyes, and so it'll pick up the signal, and then the receiver is actually going to process it and send it ultimately to your computer. You can buy these receivers pre-tested and pre-built, or if you're electronically inclined, I think you can buy the kits where you can sort of solder all these pieces together yourself and sort of build the receiver from scratch. Personally, I'm not that electronically inclined. I have kind of a reverse Midas touch when it comes to electronics sometimes, and so I just I prefer to get the pre-built tested receiver, and so we've got that on hand. And then on the back of that receiver, you can see some various plugs available. So your antenna, so this is just a coax cable. This is coming from the antenna, so the signal goes into your receiver here. You have a couple RCA audio jacks here, so you can plug this one into your computer and maybe one into a set of speakers or a headset, so that you can just listen directly to what's coming out of the receiver. And then a power supply, and so it hooks up to a DC power supply like a battery. And so off on the side here, you see a little lantern battery, a little 12-volt battery. Battery is usually the better way to go for direct current, because when you get into things that are running off of AC, that can throw off a lot of radio frequency interference. And so a battery is something you might want to get to run things off of. Of course, if you're using a laptop to do all this, you probably have it running off a battery as well, which is also advisable. But what else do you need? Because you need to attach all that wire and coax cable to something, and you've got to sort of string it up. And so you've got to do it with some mass. The general plans that we've used is the PVC pipe. So we've got several different types of PVC pipe of about 10 feet length. And we fit one into the other and we make it extendable, and we use the various bolts to secure it, and some attachments to attach rope to for guy lines, and some stakes not pictured here that you would perhaps put into the ground to hold the thing up, and some cap ends and some other nuts and bolts that you need to put together. So this is one antenna. And so this is kind of not what you would think of when I mentioned we're making a radio telescope. Perhaps when you think radio telescope, you think of sort of like the dishes that people have for DirecTV or any of the satellite television providers, or the big radio dishes you see at various observatories around the world. It's not that type of telescope. In fact, if you look at it as a simple sort of antenna, you might not think it's a telescope at all. However, when you construct it in such a way and you actually use an array, some of them in tandem, it actually does concentrate on an area of the sky and sort of amplify the frequency you're interested in. And so in that directionability and that amplification of what you're wanting to look at really does make it a telescope. It's just not optical. And it's not steerable, so basically you have to set it up and sort of set it and forget it. You really don't have too much adjustability to it, other than perhaps the way you design the mass. You can make them perhaps where you make them taller or shorter. And so this height above the ground here, typically the design is made where you can adjust it from about 10 feet high to about 15 or 20 feet high. And so adjusting the height actually ultimately makes adjustments to where you're looking in the sky. And I can show you a sort of an outline of where that area is. And so primarily one would adjust this based on where Jupiter is in the sky if you're trying to follow Jupiter. It may also need to be adjusted based on what your latitude on Earth is, because if you're really far north of the equator, you might need a much higher antenna. If you're closer to the equator in the southern part of perhaps the United States, you might need a shorter antenna. So 10 to 15 feet will work for you perhaps in Florida, whereas up here in Indiana or further north, we might need to be 15 to 20 feet. It also depends on where Jupiter is. It's not always at the same height above the southern horizon. It's designed to pick up 20.1 megahertz. This is an interesting frequency because it's not dominated at that particular frequency by any local radio stations. However, there is a 20 megahertz, I believe there's a 20 megahertz radio signal coming from WWV, which is the astronomers used to use this shortwave radio station of this frequency or some of the other frequencies it broadcasts on to actually synchronize their clocks. Of course, now with the internet and everything, clocks are pretty well synchronized, so we don't really do that too much. But if we have time, I can even dial it up for you and have you hear what you can actually dial it in and listen to it on the phone, and you can hear a ticking of a clock. It's an atomic clock that keeps perfect time, and then it'll have a tone every hour and tell you what the time is, and so you can synchronize your clocks that way. So that's what we used to do. But that 20 megahertz is one of the stations. So you could test your antenna and sort of like during the daytime, you could sort of where you would expect to perhaps hear some of this stuff better because of the condition of the upper atmosphere of the Earth gets fairly reflective of radio waves in this area, and so you might be able to pick that up. So actually broadcast out of Colorado. But in our Radio Jupiter, we're not just using one, we're using two. And you have to set it up in such a way, certain distances apart, and each one is identical in terms of the length. They're about 24 feet across. They are situated, lined up directly east-west. One would be in the north and one would be in the south, separated by about, again, another 20 feet or so. And so this whole thing will fit into an area about the size of maybe like a volleyball court. And I'll show you a picture of us putting it from another institution where I put one together. This is your coax cable, which is actually split apart and attached to each of the copper wires. And then it's run down to a power combiner, which just basically brings your signals together out to the coax cable to the receiver. And this phasing cable down here in the south is used, a certain length is used to sort of, since this one is going to get the signal first versus this one, this is sort of a built-in sort of delay to make sure that everything for that frequency you're getting is combined and interfering constructively, and you get sort of the maximize your signal. And so all of that is outlined in the manual. So what would this cost you? This is sort of the base price. There's some other things that you can get to add costs, of course. This assumes you have a laptop to work this on and the ground to put the thing up. The kit itself, those parts that I showed you, runs about $300. And the software runs you about $20. I'll show you some of the software that you can use. That includes the strip chart that we were looking at earlier for the signal strength. And the mast hardware, this is stuff you pick up at Home Depot or Lowe's. It's gonna run you a couple $100 at least. I think we might have spent a little extra to get all the tools we needed too. So if you need tools, you don't have to add to that. So that gives you an idea of the costs. And this was all funded by the Physics and Astronomy department. So they were kind enough to provide the funds so that we could build this. I'd like to credit the students, undergraduate and graduate students. They were also part of my Astronomy 380, 580 topics in astronomy course at Ball State University this past semester. Richard Gorby and Melanie, Alec, Nicolette, Brielle, and Belle. Some of these were graduate students that were helping out, and some of them were undergraduates and graduate students that were in this course. We actually have sort of a club or interest group on campus, and we have a Slack channel, if you know what Slack is. You can email us and get added to the Slack channel if you'd like, where we try to get the students to work with astronomy in general, not just Radio Jove, but we do have a Radio Jove channel. And we still have yet to completely build the antenna. We have one step or two left, and then we still need to test it. But once we do test it, we hope to have a permanent home for it, not directly on campus, but just off campus on the northwest part of town, an area called Cooper Farm, where there's some property that the university rents out. And there's a facility that houses sort of a classroom for this area. They bring students here, and it's a visiting area for the Cooper Farm. And it has a lot of sort of open land here. There's actually a sort of a house over here to the left you can't see. But we were hoping that we could probably use some of this empty land here to construct the antenna and then run a cable over to it and house our receiver and our computer. One thing that we're a little concerned about, we haven't tested this yet, is inside here, you can't see in the shadow, there's actually sort of a closet, which I've zoomed in here, that houses all the electronics for the solar power that it runs off of. Now, this sounds all nice and neat and everything. However, the inverters associated with solar power, it's charging up all these batteries and everything, and then there's outlets inside the building for electrical power. It can throw off a lot of radio frequency interference. And so we have to kind of test things and see if this is a problem. We might have some sort of way of shielding this area with some copper mesh screen, or even maybe chicken wire to sort of create an electrical grounded cage that might block the radio frequencies from interfering with the telescope. So some neat stuff that we might have to look into. If it becomes too much of a problem, we might have to look for another location. So if anybody knows of a good place in Muncie where we could permanently put something up, let us know. The nice thing about this area too is it has Wi-Fi, and so we have the sort of infrastructure to set it up and maybe access it remotely from campus without actually physically being there. Then of course we can take trips out there to do some hands-on stuff from time to time. This is just a little sort of automated show showing the construction. I originally set this up about 11 years ago at my previous institution, which was Francis Marion University in Florence, South Carolina. And there was an observatory at the sort of south end of campus that was near some baseball fields and softball fields. This is not Ball State here, but again, this is Francis Marion University. But you can see the students setting up the two dipoles here. And you get the idea of the scale. You got the ropes. You can barely see the copper wire string across. And this thing's pretty sturdy. I had this thing survive a glancing blow from a hurricane some years ago. One of the masts fell down, but I was able to re-secure it. And there's the laptop connected to the receiver, some speakers over on the side. Now we added a little extra funding and had the area cleared of grass, so we didn't have to worry about mowing, laid down some gravel, and actually fenced in the area because we had public nights out here and we didn't want people to be tripping over these ropes in the middle of the night. We also strapped some solar lights around the area, little lamps. And before we got up and running, I thought it was interesting because some Radio Jove members actually picked up a solar outburst. So here's the classic shark fin looking thing. Again, I don't know exactly which type of outburst this was, but this was at 20.1 megahertz, which is ideal where the receiver is going to pick things up. And this outburst happened on February 9th of 2009. What was really interesting about this is this was during a solar minimum. Solar maximum wasn't expected to start until about 2012. And even that was sort of didn't happen until more like 2013. It was a long minimum, kind of like what we're in now. And so there were no sunspots. And so I looked into it, and it's like, this is an example of, I went to spaceweather.com, which is a great website to see what's happening with the sun on a daily basis, and they have an archive. And so I pulled up an image of the sun. And so over here on the left, this is kind of a visual, an optical image taken with a filter. And you can see there's no sunspots. It's just a blank solar image. However, around that same time, this is an image taken from the Stereo spacecraft, which was a pair of satellites that led and lagged the Earth's orbit, so it could kind of look at it from two different angles. I think one of the spacecraft lost contact some years ago, but they clearly saw in the extreme ultraviolet this active region here. And so this was an outburst that didn't seem to be associated with spots, because typically you would have activity associated with spots. And those are magnetic activity things themselves. You have magnetic flux lines coming out of the sun at the foot point where a sunspot would be. And then it goes up into the upper atmosphere of the sun and back down into another spot. And so normally you don't see this kind of activity without some spots being present. So there's some interesting solar studies that can be done as well. Now this is just kind of interesting because I was pointed, someone pointed this out to me recently, that you can do some research, and this is a recently published work using radio Jove that is not even anything to do with Jupiter, the galaxy, or the sun. And so they were actually detecting sort of frequencies, radio frequencies in the 15 to 30 megahertz range where radio Jove operates, and they were actually detecting lightning strikes from remote thunderstorms. And so this is all part of the citizen scientists initiative as well. And this was published in Geophysical Research Letters just this a couple months ago. The software I mentioned is pretty interesting. It allows you to make predictions of when you should go and observe. Now this is a kind of a complex plot. It's actually plotting effectively where Io is around Jupiter, and then the x-axis is where what the orientation of Jupiter is for its magnetic field. And so you can sort of correlate them into different areas on this plot. And these sort of blobs here with the darker orange or red are areas of high probability of storms. And so you have what's called IOB, IOA, and IOC. And so depending on where Io is around Jupiter, you might get one of these sort of events. And so you can use this tool to determine when to go out and observe. These diagonal lines that cut across here have hours on them in 24-hour time. And then the little icon of Jupiter basically tells you what time it is. So this would be something around just before perhaps 1:30 in the afternoon for a particular date. And you can see Jupiter's in this area. These are low probabilities, so you wouldn't expect to get any Jupiter storms at those times. However, later on that night, around 22 to 2300, Jupiter would be in this area, so you might be able to get these IOB storms. So it basically gives you a predictability. So we have a way of knowing when to go out. It's not just random. With solar emissions, you have no warning. It's just that they're going to happen almost randomly, and so you have to just have the thing on and lucky to catch it. This is software by Jim Sky, and so you can go to radiosky.com and you can pick this up. I think it has a 30-day trial period, and then it does ask for you to purchase it for a small price. And in addition to that, this is the tool here. Same program, but a different tool, multiple tools inside of it. This gives you an idea of, this green circle is the area that a properly constructed radio Jove antenna array will concentrate in the sky. So it's the southern part of the sky. So this is the entire sky. So this is the northern sort of horizon. This is the southern horizon, west on the right, east on the left. This line cutting across here, I believe, is the celestial equator, and or perhaps, let's see, is that correct? It should be set for our latitude. I believe I pulled this up. Yeah, so we have Muncie at 40 degrees latitude, longitude 85 degrees. I set it for, I think it was early tomorrow morning at 3 a.m. And so here's Jupiter in the sky. So this is actually accurate star field. And you can see that Jupiter's low in the sky, but this green oval tells you where your signal is being concentrated on. So they call it the beam of the radio telescope, right? These green lines here just indicating the orientation of your dual dipole antenna, right? Running east-west, one on the north side, one on the south side. So that's pretty much it. And here's the useful links here for Radio Jove, and then the citizen science initiative that Radio Jove is recently getting associated with. And you can see the logo that we have, or that Radio Jove has, that I actually have as part of my Zoom background, is kind of a neat, gives you a neat sort of graphical description of what was really going on for Radio Jove, that we're actually picking up some of the magnetic fields and material flowing from Io to Jupiter. And these are some of the names associated with the project. And that pretty much concludes my talk.
Thank you, Todd, and thank you again, Nicolette. So if you're just joining us, we have Dr. Todd Vaccaro from the Department of Physics and Astronomy at Ball State University, as well as Nicolette Terrasciano, an undergraduate student at Ball State who helped with the Radio Jove project that they're trying to set up. And if you have a question about the presentation, you want to know more, just put that in the chat and we'll get that to Dr. Vaccaro and Nicolette for try to get some answers for you. There is a little bit of a delay, so please be patient with us. And while we wait for any questions or comments in the chat, I have a question. So I was wondering if you think that listening to the data that you get in, so we heard some of the audio from the Radio Jove project and other types of data that was collected from other observations. Does listening to that data add value to the science, as in when you're processing and analyzing this data? Does listening to it help see things that you wouldn't otherwise see, do you think?
Right, I mean, that's a good question. That's the purpose of the archive, I believe. There are other people doing different studies, and like I said, this is a pretty flexible tool, and so some people might be interested in certain signals at certain times, and so they might go back through the archive and see what other people have picked up, and so the data is there for them to use. So you know, all sorts of different things that you could use it for. A particular project, for example, might be one that I've read about that sounds pretty interesting, is if the sun is relatively inactive, one of the nice things about radio astronomy is you don't really have to worry about the weather as much, because radio signals are going to get through even if it's cloudy. And so it's not like an optical telescope where if it's cloudy, you're not going to be able to observe. And so that is also true in the sense of, if the sun's not active, theoretically, even if Jupiter happens to be somewhere in the daytime sky, you might be able to observe or detect signals coming from Jupiter. And where I thought there was an interesting thing, because myself as a stellar astronomer, I'm interested in the effects of stellar astrophysics. If you had Jupiter lined up pretty close to the sun, not obviously behind it or really, really close, but pretty close to the sun, if you were detecting some of those radio waves, it might be passing through the sun's upper atmosphere called the corona. And you could use the radio signals from Jupiter to sort of probe the sun's atmosphere. And that's an interesting notion. So something like that would be maybe a little bit more of an advanced project, and some of these would take time, but that would be something that you could do as a project. But supporting other things, you could even argue that some of the ground-based observing could support some of the Juno data. So if they're collecting data at a certain time and you happen to have data that was covered around the time that they were observing some aspect of Jupiter physically being there as part of Juno, they would be able to sort of take that supporting ground-based data and analyze it in conjunction with what's going on there. So I think the possibilities are kind of endless, and you never know what you're gonna get. I mean, if you think about the history of Radio Jove in the first place, someone was basically trying to get some data on the Crab Nebula, and next thing you know, that they're exploring the magnetosphere of Jupiter.
Great, thank you. We have another question from Riley. They want to know if you would get a performance cut, or how much of a performance cut you'll get if you mount a single dipole indoors. So say you live in an apartment and you want to try to get some data from inside that apartment.
Yeah, indoors I wouldn't recommend.
It says we're live.
Okay, we're back up.
Yay!
All right. So again, we're trying to answer the question from Riley, asking if you could mount this indoors. And Todd, go ahead.
Right. I think that when you do a single dipole, you're really looking at almost the whole sky, and it's not going to be very good for Jupiter. You're probably going to be swamped by radio frequency interference from things inside, electronics inside. You probably would be able to pick up solar flares, because when that happens, it's going to swamp everything because it's pretty strong. But as far as Jupiter, you probably would have a hard time.
Thanks. Do you know when the Radio Jove project at Ball State is going to be up and running, or do you have a time estimate for that?
That's hard to say, because we were in the process of building it when all of a sudden the COVID-19 stuff happened, right? So the lab's been mothballed since March. No one's been in there, and we still need to split the coax and attach it to the wire. But once we do that and solder some pieces, we can just take the thing outside and test it on the quad out on campus and see what we get. I know that the campus, I don't think, is officially opening in any sort of capacity until maybe July. So July is around the time that Jupiter is at opposition, which is a prime time for observing Jupiter because it's on the other side of the sun relative to the Earth. And so it should be rising around the time that the sun is setting, and we can go out there some early evening and play around with things and see what we get. So maybe July. If not, we'll definitely try to have it out and maybe even do some public events during the spring or fall, this fall.
Okay, and again, if someone wanted to become involved with that project, what would they do?
Either contact, if they can contact the department, myself, they can contact you, and then we can maybe get them on the Slack channel, and if they're local and they want to be part of it, that would be great.
Great, yeah, and if you want to just contact the Planetarium, our email address is planetarium@bsu.edu, and we'll get you in touch with the right people to get that process started. Anything else that you two want to add before we wrap up today?
Pretty much good. I mean, if you guys have any questions, I have hands-on experience. If you guys want to get involved and you're a Ball State student, you know where to find me. You just type in my first name and my last name, which is on Facebook here now, so you can find me. Just go ahead and ask.
Great. So Alyssa's
we'll
saying that this is really fantastic, and she hopes that we do a public event sometime soon.
Cool.
Sorry, Todd, did you have something else?
No.
Okay.
I was just saying Nicolette can be in charge of the student organization.
Oh yeah, I'm fine with that.
Wonderful. All right. Well, thank you so much, Nicolette and Dr. Vaccaro, for joining us today. We really appreciate having you both here and your expertise on the Radio Jove project at Ball State University. My name, again, for those who might not know me, I'm Dana Thompson, the director of the Planetarium. And next week, we're going to be talking about Saturn. I'm going to be doing a presentation for our next live presentation for the Your Universe series. The next 2 weeks, we're going to be talking all about Saturn and its moons, because Saturn now has the most moons that we know about in our solar system, with 82. And we'll see you, hope to see you then, and we'll see you online before then with lots of other posts for Your Universe series. If you have any more questions or want to get involved with the Radio Jove project, again, you can just put your questions in the chat or email us at planetarium@bsu.edu. Have a great day, everyone.